have seen the perturbed equation of motion using stability axis system, and last lecture you have seen it is derived one equation along the x-axis. Now today we will be doing along z-axis, or it's a z equation, because we are talking about longitudinal motion. That is why we are talking about x, z, and motion about y. So the equation is, you see the Sixdorf equation, it is fza, or what sort of I write it? Place mg cos theta cos phi is equal to m w dot plus pv minus qw. Okay? Now you are expert, we will introduce perturbation. So how do I introduce perturbation? For fza, what I write? Fz A1, that is aerodynamic force acting along z direction at steady state, that is 1, plus because of perturbation there is a force Fz. Similarly for mg, here it is cos of theta 1, that is steady state plus perturbed theta, into cos of phi 1 plus phi is equal to m. Again here w1 plus small w dot plus p1 plus small p, very mechanical, okay, into v1 plus small v minus q1 plus small q to v1 plus small v. Please understand that we are, this is not v, this is qu, sorry, u, so this will be u1 plus small u. Okay, very boring. See, you could see from my energy level here, I am getting tired of writing all these things. That is why you are the younger generation people, you should take pen and pencil, and whatever I am telling you, you derive it, okay? And you have to do it once, I am telling you. Do it once and forget it. Then remember the final result, understand the physics of it, and go for designing an airplane or analyzing an airplane. So this is the perturbed equation. We have introduced perturbed quantities. Again, we will see whatever way we did last time, that at steady state, right, this fza1 plus mg cos theta 1 cos phi 1 was equal to m w1 dot plus p1 v1 minus q1 u1. So use this, expand this, use this, and also use the product of two small or perturbed quantities can be neglected, and if you do a similar mechanical way, you will get second relation as, let me write it here, you get fz minus mg theta sine theta 1 equal to m w dot minus q u1. So what we will get is fz minus mg theta sine theta 1 equal to m w dot minus q u1. So this is your second equation, and try to understand what are this equation means. Fz means the perturbed aerodynamic forces along the z direction, so body fixed direction. Theta is the perturbed quantity. Theta 1 is the steady state value of theta during at equilibrium, and w dot is a perturbed acceleration. Q is a perturbed quantity. Right. So similarly, you could see the third equation, which is pitching equation, is I y y q dot equal to m, pitching moment, and this you could easily see that this I can write as I y y q1 plus q dot equal to m1 plus m. What is q1? q1 is the pitch rate at steady state, but at steady state, what is q? Q is 0, because airplane is going like this, there are no pitch rate. So this man will vanish, and here m1 is the pitching moment at steady state. Since the airplane is at trim, the m1 will be 0, but perturbed quantity m will not be 0, because as you disturb, airplane will do like this, right, and try to come back, or it may diverge. So this man will not be 0, but at steady state m, the pitching moment will be 0. That is how we define trim. So if I do that, then I get Iyy q dot equal to small m. Simply this is 0 and this is 0. Very simple. So what did we get? You see how beautiful equations we got after doing all those juggleries. And what is important for you, remember those equations and try to develop feel for those equations, and we will be doing that. But as I have always been mentioning, once you have to write this equation, expand it, and the class 10th, 11th level, you should be able to get this. So what are the equation you got? Fx minus theta into mg cos theta 1 is equal to m u dot. Then fz minus mg theta sin theta 1, mg theta sin theta 1 equal to m w dot minus q u1, and of course you also got Iyy q dot equal to m. These are what? These are perturbed equations of motion longitudinal case. Also remember, when we are deriving this first equation, we have assumed that we are writing stability axis system. The x-axis is pointed toward the velocity vector. So you must also note down stability axis system. This has made this equation simpler. Now this is the equation. So what is our aim? Our aim is to see how to analyze dynamic stability of an airplane. And you could see here, Fx is the aerodynamic force, perturbed aerodynamic forces, and theta again a perturbed quantity. All are the perturbed quantities. What does it mean? That if there is a disturbance through Fx, Fz, or a moment, then how perturbed quantity q, or here w, or here theta, or u is going to vary. If it comes down to 0, then we say it is dynamically stable. Suppose I am going like this, sir, there is an aerodynamic force because of angle of attack disturbance came. There is aerodynamic forces will come, Fx, Fz, and moment. This will create a response in terms of theta, perturb u, and perturb w. And if I solve this equation, if I find this perturbed quantity vanishes, comes back to 0, when the disturbance is withdrawn, then I know it is dynamically stable. If it goes otherwise, we say it is dynamically unstable. So what is called for is, I need to solve this equation. I need to model what is Fx, Fz, and m, how to calculate Fx, Fz, and m. Once I know that, then it is simply solving any differential equation, simultaneous differential equation, right? Okay? So please understand, we have come very close to developing an equation where equations of motion, where you can have our own control. Yes, now I know this airplane configuration is going to be dynamically stable or not. And if you want to change the handling qualities, if you want to change the natural frequency, if you want to change the damping ratio, I know how to do it. Okay? This will give us so much of information, and that is why we are putting so much of time to write all this nitty-gritty and doing all those steps, which you may not like. At least I don't like writing all those equations. Okay? We have developed perturbed equations of motion, longitudinal case, and we have assumed stability axis, and you could see that this equation became very simpler, because for stability axis assumption, W1 is 0. Now, I again repeat why we have developed this equation, because we want to see whether the aircraft is dynamically stable or not, and we need to solve this equation in terms of u, the perturbed u, perturbed theta, and perturbed q. And I want to see that how this u theta q, perturbed u theta q varies if it vanishes. And then we say it is dynamically stable, they are dynamically stable. And what are these fx, fz and m? These are perturbed force along x direction, perturbed force along z direction, and perturbed moment about y axis. Okay. So let us see this perturbed force fx. That will depend upon what? That will depend upon, you could see that it could depend upon u, depend upon alpha and delta E. Very simple, because if u is there, then there is a dynamic pressure change, half rho u square. So it will, fx will depend upon u, fx will depend upon alpha, because if there is an alpha, there will be a CL and CD, that component will come on x, and then delta E, of course, as we deflect the elevator, that will also change the little bit of CL and little bit of drag. So it's not a bad assumption to write fx function of u, alpha and delta E. So similarly, fz, also we can write function of u, alpha, delta E. And sometimes, you will see that it will also be function of alpha dot, and we will explain you why alpha dot is being included, and sometimes it is neglected also, and we will discuss as we progress. And the m is of course function of u, alpha, then alpha dot and delta E. So let me write delta E at the corner so that it makes our life simpler. Why I have written delta at corner is because we will treat delta E as a control input, and u, alpha, alpha dot, they are all what we call our motion variable. But if you see here, we have missed one very important derivative in the moment. Okay? We have seen that it's not only an alpha, at steady state there is an alpha that would give you a moment, but as it moves like this, because of q, there is a damping comes from the tail, primarily from the tail. We have seen that. That is, if I take this tail, and this is the CG, we have seen if there is a q, then relative air will come here, and that will give a moment and force. You could see that if there is a q, there will be a force experienced by the tail in the opposite direction as it goes down. So the force as well as the moment, pitching moment, will be function of q predominantly. So I have to put here q as well as here q. So what is my modified thing? Modified thing is fz is function of u, this is comma, u, perturbed alpha dot, perturbed q, pitch rate and delta E. And pitching moment is also function of perturbed u, perturbed alpha dot, perturbed q and delta E. Okay? So this is fairly a good modeling, okay, for small disturbances, small perturbation. Now, the question is, since we have assumed it to be a case of a small perturbation, we want to take advantage of linear aerodynamics. And then how should I expand fx? We'll write fx as df. So we'll expand fx taking the advantage of linearity, and add dfxa by d alpha into alpha plus, or let's say first u, first I write dfxa by du into u, then plus dfxa by d alpha into alpha plus dfxa by d delta E into delta E. So what is the meaning of this? The perturbed force can be modeled if I know that derivative dfxa by du at steady state, the partial derivative, I can get fx if I know dfxa by d alpha at steady state. I can know if I know that dfxa by d delta E at steady state. This is important, right? So this is typically I am taking advantage of a linear expansion, right? But there's another thing you should observe here, that alpha, what is the dimension of alpha and delta E? They are dimensionless, radians, dimensionless. But what about u? U is meter per second. Okay, whereas alpha and delta E are dimensionless. So, but we want to write the whole equation in terms of a consistent, in terms of dimensionless motion variable or control variables. So what we do, trick is we write u as u by u1. Okay, so what is this u? Whatever u is there here, I replace it by u by u1, and then you could see I could rewrite fx as dfxa, the change in aerodynamic force because of du by u1 by u by u1 plus dfxa by d alpha into alpha plus dfxa by d delta E into delta E. Now you could see that everything is this alpha, delta E, u by u1 all are dimensionless. Right? Let us again come back to this. What is the meaning of this term dfxa by du1? This is the dfxa by du by u1. This is the partial derivative evaluated where? Evaluated at steady state. This is also evaluated at steady state. Evaluated at steady state. You will see what is the meaning of this once we try to develop an expression to calculate dfxa by du by u1. Okay. Similarly, for fz, what I can write? Fz will be dfza by du by u1 into u by u1. You are now expert. dfza by d alpha into alpha plus dfza by, if I write d alpha dot into alpha dot, again you will tell me, sir, what is happening? This is again alpha dot and q, they are dimensional quantities. So how you are writing like that? I agree, your point is correct. So we will do some correction. So mechanically, if I expand it, it will be dfza by du by u1. So you have seen it should have been dfxa by du. So you have agreed that I will replace u by u1. So this becomes this. Alpha is fine. But the moment I come to alpha dot, dfza by d alpha dot into alpha dot, I find this man has radians per second. So it has a dimension, and q is also radian per second. It has a dimension. So I have to make both of them non-dimensional to be consistent. So what we do? We do a simple trick. So we do a simple trick. We write fz equal to dfza by du by u1 into u by u1 plus dfza by d alpha into alpha. No problem, everything is fine. But the moment I come to dfza by d alpha dot, I write it like this: d alpha dot c by 2 u1 into alpha dot c by 2 u1. Again you see alpha dot, I have replaced by alpha dot c. C is the chord by 2 u1, and that is a non-dimensional quantities. And similarly I write dfza by d, for q I write qc by 2 u1 into qc by 2 u1 to again take care of the dimensional aspect, and then we have dfza by d delta E into delta E. Again, if we come back to this expression, what is the meaning of dfza by du1? This is the partial derivative evaluated at steady state. Again, partial derivative evaluated at steady state. Here again, partial derivative evaluated at steady state. All are evaluated at steady state. Okay, so now this is clear to you as far as mathematically expanding it. We will try to give physical interpretation of these derivatives, and then we'll find how simple, how wonderful are these things. And then for m, again we write m as function of u alpha dot delta E. Now here becomes smarter, so we write f is function of u by u1 alpha, alpha dot c by 2u1, and of course q is there. So q c by 2u1 comma delta E. Right? What we have done? We know that finally we are going to change alpha dot and q to alpha dot c by 2u1. So we are now just mathematically, we have placed u by u1, alpha dot as alpha dot c by 2u1, and q as qc by 2u1 and delta E, to make our life simpler. Okay? So now if I use this and if I write the expansion, what do I get? Then I get m equal to dm by du by u1 into u by u1 plus dm by d alpha into alpha plus dm by d alpha dot c by 2u1 into alpha dot c by 2u1 plus dm by dq c by 2u1 into q c by 2u1 plus dm by d delta E into delta E. And again, if I repeat, what is the meaning of dm by du by u1 and all these partial derivatives? They are the partial derivatives evaluated at steady state. At steady state, that is at equilibrium, about which I am giving the perturbation. Right? There, at steady state. Okay? So you may suddenly start thinking alpha dot c by 2u1, why not alpha dot c by u1? You are fine. As a matter of convention, 2u1 has been taken. German do take, sometimes they take alpha dot c by u1. For us, all this convention mostly agreed it is alpha dot c by 2u1, right? qc by 2u1, two factors there. Okay. So this is the expansion. What is important for us to understand? How do I evaluate these partial derivatives? Okay, and that all these partial derivatives. So we'll start with the process of calculating these partial derivatives so that it gives physical feel for you rather than writing some expression blindly. Okay, let's do that. Let me segregate and write alpha derivatives. What exactly we are talking about? We're talking about dfxa by d alpha, then dfza by d alpha, and dm by d alpha. Let us see physically what does these mean and how to evaluate them. Let us start with dfxa by d alpha. dfxa by d alpha. Let us draw a aircraft. Let this is the axis system, and let there be an alpha. Okay. So what is fxa? Right. What is fxa? fxa will be minus d cos alpha plus L sin alpha. You could see that if this is V, then drag will be here and lift will be here. So in general I can write fxa as minus because of d, right? Minus this component will come here, so minus d cos alpha, and from L you will get one component along x direction, so L sin alpha. Okay, no issues on that. This is the d cos alpha, and L, one component will come in this direction, which is L sin alpha. So that is how. Why minus d cos alpha? Because it's in the opposite direction of x. Right. Now if I find out dfxa by d alpha, what do I get? I have to take the derivative. So what I do, minus q infinity s then this I write as, or before I do this, to make sure that you are not getting lost, I write this in another one step is minus q infinity s, and I put it here CD cos alpha minus CL sin alpha. No objection. I have taken minus half rho v square s out, so half rho v square s, CD is this, CD cos alpha, minus is here, so plus here, so minus is here. Now I take derivative dfxa by d alpha. What does this mean? This will be minus q infinity s, okay. This is first term dCd by d alpha into cos alpha, then I keep CD minus CD into cos alpha is sin alpha. See, the derivative of cos alpha is minus sin alpha, so that is why this minus sign has come here, okay. Then for this minus CL or dCl by d alpha, dCl I take derivative into sin alpha, okay, dCl by d alpha into sin alpha, then minus CL into derivative of sin alpha is cos alpha. No objection? As simple as that. dCd by d alpha into cos alpha, then CD, derivative of cos alpha is minus sin alpha, so minus CD sin alpha. Second term is minus CL, minus dCl by d alpha sin alpha, then minus is there already, and CL, derivative of sin alpha is cos alpha. Now what is the story? Story is we have to evaluate dfxa by d alpha at what condition? At steady state, okay. So I have to calculate. If I erase this now, erase all these things. So I have to calculate dfxa by d alpha at steady state. That will be what? That will be minus q infinity s, I write CD alpha at steady state. What are these alpha? Alpha is perturbed angle of attack. So at steady state, what was the value of perturbed angle of attack? At steady state, it is 0, right? So this is cos alpha is 1. So at steady state, this alpha is 0 because there is no perturbation at steady state, only we are evaluating at steady state, right? So that time it is a alpha 1. So there is no perturbed quantity. So this is cos alpha, cos 0 is 1, minus CD sin alpha, so this goes. So this is minus 0, this is again minus 0, and minus CL. You see, at steady state, this perturbed value of alpha is 0, so this cos alpha becomes 1, this man goes 0, this man goes to 0, this is minus CL. So you have dfxa by d alpha evaluated at steady state is equal to minus q infinity s into CD alpha minus CL. And further write this as dfxa by d alpha evaluated at steady state is equal to q infinity s into CL1 minus CD alpha. Do you see why I put 1 here? Because this is evaluated at steady state. At steady state, alpha is 0, but the CL will be corresponding to CL1. That is CL at steady state. And this minus sign, I absorbed it there, so I get this expression dfxa by d alpha as this. Is it anyway very difficult for you? No? Half rho v square at steady state, you know, the aircraft cruising, half rho v square s, you understand what is this? S, you understand. CL1 will be what? CL1 means CL at steady state is nothing but 2W by S by rho v square. Okay. What is CD alpha? CD alpha is CD equal to CD naught plus KCL square. So you can easily find out dCd by d alpha from here by taking the derivative. So these are all known for us. So simplified expression we get for dfxa by d alpha. Why we are all evaluating this? Because we have to put those expressions here. dfxa by d alpha, I have to replace it by Q infinity as CL1 minus CD alpha. We will evaluate all these derivatives, right, and try to substitute them by such expressions.